The era of fragmented visual generation, where you need one model for images, another for video, and a whole bunch of different fine-tunes for editing that might finally be coming to a close.
It really might be. Today, we're diving into a paper that's a huge step in that direction. It's called VInO, a unified visual generator with interleaved omnimodal context.
And the problem it's tackling is one we see everywhere in generative AI, right? This massive inconsistency and complexity because every model is just stuck in its own silo.
Exactly. VInO's big breakthrough is integrating image generation, video generation, and really sophisticated multimodal editing all within a single diffusion framework.
And the way they pull this off is by coupling a powerful frozen vision language model, in this case Qwen3VL, with a multimodal diffusion transformer, or MMDiT, that they initialized from the VInO video model.
Right, and the real engineering magic is in what they call the interleaved omnimodal context pipeline. To get text, reference images, and videos to all play nicely together, they introduce 3 really clever mechanisms.
Okay, what are they?
So you've got learnable query tokens for training stability, VAE latent injection to keep all the fine-grained details, and a new token boundary mechanism to keep the static and dynamic inputs from getting tangled up.
And the results are pretty stunning.
Yeah.
VInO doesn't just maintain the quality of the base models it was built on. It actually dramatically improves performance on really tough tasks, like multi-reference grounding, following long instructions, and this is the big one, keeping an identity consistent across both images and videos.
It's a fundamental shift. We're moving away from a whole bunch of specialists towards a true generalist model for all things visual.
So let's talk about that mission of unification. I mean, why go to all the trouble of forcing everything into one model?
Well, if you look at how things are now, the control signals themselves are often in direct conflict. For text-to-video generation, you need these rich descriptive captions, describing the lighting, the mood, everything.
Right. But for editing, the instruction's totally different.
Totally different. It's short, it's imperative. Remove the dog, or make the car red, and that creates this fundamental semantic conflict between a rich description and a sharp command.
Which usually means you need separate models or really clunky workarounds.
Exactly. VInO's architecture just gets rid of that fragmentation. Instead of different modules for different tasks, it's one shared MMDiT backbone. And crucially, they unify all the conditioning signals.
The text, the reference images, video clips, all of it.
All of it. It all gets routed through a single, powerful vision language model encoder.
So the VLM is acting like a universal translator for all the incoming context.
That's a perfect way to put it.
Right.
By using a pre-trained VLM like Qwen3VL, they're tapping into this massive existing knowledge base. The VLM takes all these different inputs and translates them into a single coherent sequence of conditioning tokens.
And it's that sequence of tokens that guides the actual generation in the MMDiT. So you're architecting for many-to-many kind of creation.
Right. You could feed it 4 reference images, a video click for motion, and a text prompt all at once. And the model is designed to process them coherently.
Okay, let's unpack that process. So the VLM is the front end. How are the inputs actually organized so you can do that kind of complex referencing?
They're very deliberate about it. They structure the prompt, giving a unique ID to every single visual input. So you'll have image 1, image 2, video 1, and so on.
And that's not just for organization, I assume?
Not at all. It's functional. It lets the text instruction be super explicit, like replace the object in video 1 with the style from image 3. The grounding becomes incredibly powerful.
That makes perfect sense for following instructions. So what's the first new component they added to make this all work smoothly?
That would be the learnable query tokens. These are special tokens they append to the input that goes into the VLM.
And what do they do?
They're essentially dynamically optimized placeholders. They aren't tied to any specific word or image. They act as this flexible interface, sort of absorbing the general context of the instruction and bridging the high-level meaning from the VLM with the low-level features the MMDiT needs to work with.
So they're like little tuning knobs that help stabilize the whole process when you're mixing all these different tasks.
Precisely. The ablation studies in the paper really prove it. When they took these tokens out, the training became way noisier and stability just plummeted. They're like shock absorbers for the whole system.
But there's a classic problem with relying only on a VLM, right? VLMs are built to understand semantics, which means they compress visual information. They throw away details to get the big picture.
100%.
So if VInO wants to do pixel-perfect editing or preserve an identity perfectly, VLM embeddings alone feel like a huge bottleneck. You're losing structure.
That's the crucial tension they had to solve. And to get around that VLM compression, they introduced the second key component, VAE latent injection.
Okay, so what does that mean?
It means they complement the VLM's semantic tokens with the VAE encoded latents of all the visual inputs, the reference images and the reference videos.
So they run the raw images and videos through a variational autoencoder, a VAE, to get a compressed version that keeps the structural details. And then they feed that directly into the MMDiT.
Exactly. It gets fed in right alongside the VLM's high-level semantic tokens. And this is non-negotiable for doing precise editing. If you want to change the color of a shirt without messing up the folds in the fabric, you need that low-level structural data that a VLM would normally just ignore.
Okay, so now we have everything going into the MMDiT. Semantic tokens from the VLM, the structural latents from the VAE, and the text prompts. But that brings up another problem, doesn't it? The VAE latents for a single static image are fundamentally different from the latents for a dynamic video sequence.
It's the heterogeneity problem, yeah. How do you put these different types of latents onto the same timeline inside the MMDiT without the attention mechanism getting confused and, smearing them together?
Right. If it confuses a static face from a reference image with the motion data from a video, you could get some really weird artifacts.
You'd get identity swapping, you'd get distortions, it would be a mess. And their solution is the third crucial component, the token boundary mechanism.
And how does that work?
It's actually really clever. They realized the VLM already uses special tokens, the start and end vision tokens, to wrap visual inputs when it's encoding them. So they just repurpose those same tokens to wrap each VAE latent block before it goes into the MMDiT.
I see. So those boundary tokens act like a structural firewall. They're telling the attention mechanism, hey, this block of data from here to here is one static image. Treat it differently than the video stream that comes next.
That positional cue is incredibly strong. The ablation study on this is crystal clear. Without those boundary markers, the MMDiT's attention just starts blending the static image latents into the temporal part of the model.
And what happens then?
You get immediate, severe artifacts, especially structural distortions that are all concentrated in the very first frame of the video. The model is basically trying to force a static structure onto a dynamic sequence, and the whole thing just breaks.
And to tie it all together, they use a Unify 3D ROPE, a rotary positional embedding.
Yes, applied along the temporal axis. This basically puts all the different visual inputs, the single reference images, the multi-frame videos, and the noisy target frames onto one shared, coherent timeline. It makes their temporal relationships explicit.
So with all this in place, VInO gets consistent grounding from the high-level VLM ideas all the way down to the low-level VAE structural details.
And that's the key. It dramatically reduces those common, frustrating errors you see in complex scenes, like a person's face suddenly changing mid-video or features from one reference leaking onto another.
Now, building a system this complex on top of a base model like Hunyor Video, which was only trained for text-to-video, seems incredibly risky. There's a huge danger of catastrophic forgetting where you just wreck the original model's abilities. How did they train it without that happening?
They were very strategic about it. They designed a 3-stage progressive training curriculum. The goal was to ease the specialist T2V model into becoming a multimodal generalist without just, overwhelming it with new tasks.
Okay, let's walk through that. What's stage one?
Stage one is all about alignment. At this point, the main MMDiT backbone is completely frozen. They only train the new little MLP connectors that they added. Their only job is to learn how to map the output from the VLM into the conditioning space that the MMDiT expects.
And how do they make sure that alignment is working?
They use what they call an image reconstruction proxy task. They feed an image into the VLM, pass the data through these new connectors, and then train the MMDiT to simply reconstruct the original image. It's a simple task that forces the VLM's visual features to align with the MMDiT's low-level world.
That makes sense. It handles the feature mismatch. So what about that semantic conflict we talked about? The long descriptive captions versus the short editing commands.
That's stage 2, bridging the distribution shift. The base model has only ever seen long, rich captions. So to get it ready for short editing instructions, they start training it on a mixture of both long and short text prompts.
And at this point, the MMDiT is no longer frozen.
Correct. The MMDiT parameters are unfrozen and start updating, which lets those learnable query tokens start to learn how to handle the concise commands. They also add another proxy task here.
What's that one for?
It's an image selection proxy task. It basically teaches the model to connect the identifiers, like image 1, to the actual visual content. So when it sees an instruction like make image 1 look like a painting, it knows exactly which visual reference to apply it to.
Okay, so you've done alignment, you've bridged the data distribution. That must bring us to stage 3.
Stage 3 is multitask acquisition. This is where they throw everything at it. The full mixed training environment, including instruction-based editing for both images and videos.
And did it work? Did they avoid catastrophic forgetting?
They did, and this is the really interesting finding. Even though the standard text-to-image and text-to-video samples were just a small fraction of the training data in this stage, the model held on to its original performance. It was still comparable to the highly optimized Honey on Video backbone it started from.
That's the proof in the pudding, really. Preserving that baseline while adding all these new skills. So let's talk about what VInO can actually do. What did the quantitative results show?
Quantitatively, it pretty much hit every target. On the big benchmarks for image and video generation, like Geneval and VBench, its performance was either the same or slightly better than the baseline.
And where did it improve?
The semantic score specifically got a nice boost. And that's almost certainly because the Qwen 3 VL model is just a much stronger VLM encoder than what previous models were using. It has a better understanding of the text.
What about the new stuff, like reference-guided generation?
On the OpenS2V benchmark, which tests how well a model can stick to a subject reference in a video, VInO showed really well-balanced performance. It proved it could successfully maintain a subject's identity through a whole dynamic sequence.
But the thing that really jumped out to me was how quickly it picked up editing. You mentioned its speed on the MMDiT benchmark.
Yeah, that was honestly surprising. It suggests there's huge value in starting with a motion-aware model. VInO got good at editing incredibly fast, after just 1,000 training steps in stage 3.
The very first time it saw editing instructions.
Right. After just 1K steps, it was already outperforming a lot of well-established open-source editing models.
1,000 steps is nothing in deep learning. That implies there was this super efficient skill transfer happening from its ability to generate motion to its new ability to edit.
Absolutely. The kind of deep structural understanding you need to generate coherent motion seems to generalize very, very well to the kind of structural control you need for precise editing.
Okay, now let's dig into some of the trade-offs. The paper talks about image classifier-free guidance, or image CFG. What did they find there?
Image CFG is basically the knob you turn to control how strongly the model sticks to your reference image. If you want the output to look exactly like your reference, you turn the scale up.
And that works for preserving identity.
It works great for identity preservation, but it's a very delicate balance.
What happens if you turn it up too high?
You start to kill the motion. If you force the visual adherence too aggressively, the model just suppresses its own ability to generate diverse movement. The videos become stiff, static, or just completely frozen. It's prioritizing visual similarity over everything else.
So you're looking for that Goldilocks zone. Enough CFG to lock in the identity, but not so much that you just get a looping photograph. That sounds like a tricky parameter for a user to tune.
It's a critical trade-off for sure. The other big takeaway from the ablations goes right back to the architecture specifically, those learnable query tokens.
Right, we know they stabilize the training.
But they're also critical for performance. When they removed them, the editing results got significantly less accurate. They turn out to be essential for any task that requires precise control, like removing a specific object or replacing something based on a detailed text instruction. They're the precision layer.
So VInO really does provide a solid, scalable path toward a truly unified visual generator. It proves a single backbone can master all these different tasks.
It does, but the paper is also very clear about the limitations. For one, it inherits the base model's inability to render clean, high-fidelity text inside images. That's still a hurdle for most of these models.
And they mentioned a data quality issue, right?
Yeah. They pointed out that the current data sets for instruction-based editing just aren't as complex or high quality as the big video generation data sets. So when they mixed that data in, it actually introduced a slight bias that reduced the overall visual fidelity a little bit. We just need better, more complex editing data sets.
But the most fundamental challenge seems to be computational, the inference speed.
Absolutely. VInO is built on a Multimodal Diffusion Transformer, an MMDiT, which uses full attention. And that means the compute complexity grows quadratically with the length of the input sequence.
So if you give it a long reference video and a bunch of high-res images, the sequence length explodes, and it just gets incredibly slow.
It becomes a massive bottleneck. It makes it really hard to use for anything fast or practical. That quadratic complexity is the Achilles heel of so many transformer models right now.
It seems like while VInO has masterfully unified the conditioning of the model, the underlying attention architecture is now the main thing holding it back from true, scalable generality.
That's a great way to summarize it.
So this leaves us with a really interesting question for the future. If the bottleneck for truly general-purpose visual AGI is now this quadratic complexity of attention when handling tons of different inputs, does the future of unified visual generation lie not in just scaling up more attention layers, but in developing entirely new architectures designed from the ground up for efficient, non-quadratic, omnimodal context retrieval?